Hi there, this is Mr. Los. I wanted to just make a quick supplemental video about how we might, without model kits, try to see a little bit about how this shape stuff works and about polarity. And I'm going to just show you a couple of examples. And it all starts with a properly done Lewis structure. I'm not going to get into how to do the Lewis structures right here. That's something you should seek me out for extra help if you're still behind on that. But for example, NH3, what I want to show you is how to use the phet molecular shape resource, which might help give us a better idea of the shape of this molecule and whether it is symmetrical or not. So as I am talking right now, in the current year, 2020, I've linked a list, or I've linked a couple different phets that you might want to look at. One of them is called molecular shape, and it looks a little bit like this when you open it up. Real molecules, what that is in some cases, it's got a handful of them here. The actual thing that you're talking about might be on here. And this, in fact, does have ammonia on it. And we can see that this is not a symmetrical molecule. And the reason I say that is because thinking of the point of view of cutting the molecule here in half this way, we've got this lone pair up here. That represents that lone pair of electrons that we saw right here. And then there's nothing to counterbalance that. There's nothing on the other side. There's hydrogens on the other side. So this is not a symmetrical shape. And it's trigonal pyramidal. The trigonal pyramidal shape is generally always polar because it's not symmetrical. Remember, a lack of symmetry is what leads to polarity. So you're looking for something to be not symmetrical to be polar. If we were doing this in the classroom, we would have kits. Now, like I said, in the case of ammonia, we actually had the thing right there under the real molecules category, but I can click over here to the other side where it says model, or if you're just first opening it up, we can go over here where it says model, and you could actually build most things. So for example, if I want to just build NH3 from scratch, I can just look at the central atom like we do when we're determining shape. It's got one lone pair and it's got 3 single bonds to it. So it already has 2 things bonded to it. I can add a third thing to it and I can pop on that lone pair. And then I get more or less the same shape that we were just looking at, the trigonal pyramidal shape. So by adding lone pairs and bonds and such to the central atom, I can get an idea of its shape, and this can help me visualize symmetry. Let's look at another example. This is one of the Lewis structures that's on one of the things I assigned at least the year that I'm doing this. This is a little bit of a tricky Lewis structure to draw, but it ends up looking like this. And so let's build this one in that model kit. Now, let's just focus on the carbon. Remember, the carbon itself has a double bond, 2 single bonds. It doesn't have any lone pairs or anything on it. So let's try that. You can click this to get rid of the bonds that you already have. So we said it had a double bond, no lone pair, right? And 2 single bonds. And this molecule, this is a trigonal planar shape. Trigonal planar molecules are often nonpolar if all 3 of these things are the same. But in the case of this one, you got that oxygen, which is up here, and it's got those 2 lone pairs, and these things are hydrogens. So we think of a plane of symmetry like kind of folding it along this line that I'm drawing right here. It is not symmetrical, and this molecule would be polar. The oxygen up on this side with those 2 lone pairs, there's a lot of negativity on this side, and there's nothing to cancel that out. So remember, polarity is about an imbalance of electrons. So this would be polar. This is another one that you have to draw on the sheet, and let's try to build this one. It might be available actually on the real molecules, but let's try to build it anyway. So let's look at the xenon here. It has 2 lone pairs and has 4 single bonds to it. Remember, we're going to ignore the lone pairs on the fluorine. And so let's just kind of eliminate everything and start from scratch here. So we said we had 4 bonds and we had 2 lone pairs. Bing, boom. This is a planar shape, a square planar shape we call it. And this thing is going to be nonpolar, and the reason is it's pretty darn symmetrical. Everywhere I look, it is evenly matched. Like there would be 2 fluorines exactly across from each other here, 2 fluorines exactly across from each other here, 2 lone pairs exactly across from each other here. So this is symmetrical in the sense of where the electrons are distributed. all the way around. So XeF4 would be a nonpolar molecule. Okay, that's all I have for you for right now. I know this is tricky stuff. As I'm recording this, we've just started looking at it, and we'll definitely look at it a little bit more. But hopefully this gives you at least a little bit of something to help you out. Thanks for watching.